What's up guys, it's me Sir Ernest, and today we're going to demonstrate to you the bisection method using an example. Okay, so here we're going to have an example on the bungee jumper wherein we want to determine the mass of the bungee jumper with the drag coefficient of 0.25 kilograms per meter to have a velocity of 36 meters per second after 4 seconds of free fall. We're going to use n equal to 3 for our stopping criteria. So just a brief recall. So when the bungee jumper is jump off your rail or jump off the bridge, okay. Of course, there's a safety rope attached to him. As the bungee jumper falls down, there are two forces acting on him. One is the downward force due to gravity, and the other one is the upward force due to air resistance. And we already calculated or determined or derived the velocity function as a function of time. Okay, so this is an equation of motion in terms of the velocity, where v, which is the velocity, is a function of time t, is equal to the square root of gm over cd times the hyperbolic tangent of the square root of gcd over m times t. Here we define these variables. V is your downward vertical velocity in meters per second. CD is a lump drag coefficient in kilograms per meter, which has a value of 0.25 kilogram per meter. The mass of the bungee jumper is m, so that is what we are looking for. And then g is the acceleration due to gravity, and that is equal to 9.81 times 9.81 meters per second squared. Now, as we notice here, everything has already been given except for our mass. So that means the only unknown variable here will be mass. So therefore, we can express this. We can rewrite this equation as a function f, which is a function of m, and that is equal to square root of gm over cd times the hyperbolic tangent of square root of gcd over m times time minus t, and we are going to equate this to 0, which is the same as this equation. Okay, also we take note of the following, that the stopping criterion, as I recall, is equal to 0.5 times 10 to the 2 minus n percent. Okay, so let's apply that in MATLAB. Okay, so let's save this as bisection example. Okay, so let's first do some house cleaning. Let's clear TLC and close all. Okay, so let's define the initial values or some values. So CD would be 0.25, G is 9.81, V is 36 meters per second, and T is 4 seconds. Okay, just to give an idea, let's define first our anonymous function. Okay, so our anonymous function would be f. So f would be a function of m, and this is equal to the square root of g times m divided by cd times hyperbolic tangent of square root of g times cd dot m divided by m times time minus v. So this is our anonymous function, and we're going to use this later when we want to plot. Let's plot right now. Okay, so let's define, let's say, a series of masses. Let's say from 50 to 200, and let's set 100 points in between those two values. Okay, so let's type in figure and then plot the mass and then f as a function of mass. And then let's use B as our value, and let's have a thick line with 3. Let's turn on the grid, and let's turn on hold so that we could add more to this plot. So let's run, and this is our graph. So you will notice that our graph increases as mass increases. So that means the graph will cross the horizontal axis at around this point. So the beauty of MATLAB is that if you set this number of masses and then you plot it with this anonymous function, we can actually identify the values in each of the points based on the defined array named mass. Okay, so we notice that we expect that by just browsing through this line, we can see that this point, that's the x at horizontal axis at 142.4, will provide us the closest value of your function. Okay, so this what I did here right now is what we call your trial and error combined with the graphical method. Okay, now so we expect that our value, the result, the mass that is needed would be equal to around 142. Okay, so now let's apply bisection method. Okay, so first let's define our initial bracket. So let's define xl to be equal to let's say 50. So this point, and then xu to be 100. Okay, so before we do the initial value, so let's apply an initial value of xr to be 0. Okay, but we're going to update it when we loop it. Now let's also define n, which is 3, so that we can easily define what es is, which is 0.5 times 10 to the 2 minus n%. And then let's have an initial value of ea equal to 1. Okay, now let's try first a for loop wherein we're going to set the number of loops. So let's say I will be 1 to 3. So let's have 3 iterations first. Okay, now this value will be our old xr. Okay, so let's define this as our old xr. xr old equals xr. Okay, and then let's compute for a new xr, which is equal to xl plus xu divided by 2. And then using this anonymous function, we're going to evaluate f at xr, which is f at xr, f xl, which is at f at xl, and lastly f at xu, which is f at xu. Now let's do two conditions. If the product of fxl and fxr is less than 0, we're going to replace the old value of xu with the new value of xr, as we described earlier. Else, if fxu times fxr is less than 0, then we do the opposite. Fxl is the one that we're going to replace. And text n. Okay, then this will be our. Now let's plot our roots. So let's say xr would be our approximate roots, and then let's place it at y equal to 0 along the horizontal axis. And let's use a circular marker. I think this is okay. Okay, so let's try. So let's put a marker. Oh, there's a syntax error here. Okay, so there's an enclosed bracket here. Save, and then let's run. Okay, so for the first iteration, I equal to 1. Right? Oh, there's an error. Oh, there's an error. XR is not. Let's just put XR here. Okay, so let's run again. Okay, now we're good. We're good. So at the first iteration, I equal to 1, the value of xr would be 125, which is the midpoint of 5 and 120. Okay, so that means, okay, if that's the case, if this is your this is your data, if this is the midpoint, so that means xr will be the new xl for the next iteration, which is what we're going to do. Okay, so let's continue. Let's run. So that is our midpoint. Okay, so let's go to the next iteration. So that means the next midpoint would be somewhere here. Is it correct? Yes, it's here. And then in the next iteration, the midpoint will be somewhere here. Okay, good. And then it stops. Okay, so after third iteration, the value of our root is very close to the to our desired roots. Okay, now let's try using a stopping criteria. So what we want to do is we want to use while. So when we say while, you're going to set a condition that as long as this condition is true, you run what's inside the loop. So for a while loop, we're going to set that EA, as long as EA is greater than ES, we are going to run the loop. Okay, but please be careful when doing a loop, when doing a while loop. Make sure that there is a, we make sure that the value will, this condition will be met soon. Okay, so what we're going to do is we're going to calculate EA. We're going to update EA, because if we do not update EA here, EA will always be number 1, and then ES would always be less than EA. So this will entail an infinite loop. So we need to put some kind of a condition, some kind of an update here. So EA is our relative error, so that's 100% times the absolute value of xr old minus xr, and then we divide it with xr. Okay, so this should be good. So let's save and run. Okay, there's an error somewhere here. Okay, there's an error here. Okay, so there is a, okay, run. Okay, so our EA here now is 100. So x old is 0 and xr is 125. Okay, continue. So our EA now will be 23%, which will plot this one. And then the next EA would be 13%. You will notice that the EA decreases. So our EA right now is 67.97. So that is our value. Let's continue again. EA will be 3%, and then 165, and then 0.82, and then 0.489, until such time that you meet the criteria. Okay, so let's remove this one. Let's continue, and it ends already. Okay, so the value of EA right now is 0.0257 because our ES is 0.05. Okay, so and then our XR would be 1.427612. Okay, now to give you an idea, let's try to zoom in to our result. Okay, so let's try to zoom in here. Okay, let's try to zoom in here. Okay, so this will be our last value. That's 1.427. 1.42.7. Okay? Okay. Now if we're going to increase, okay, if we're going to increase our n, so let's say 5, and then let's run it again. Okay, we will notice that our value of XR would be 4.27378. So this is our exact value. Okay, so if we're going to zoom in here and zoom in further, zoom in and further, zoom in further, so this will be our result. Okay, that's it. So let's just finish this with some display in the command window. So let's have display the mass of the bungee jumper should be, and then to string of XR in kilograms. Okay, then let's have another display in the second line. In order for it to have a velocity of to string meters per second after to string t seconds. Okay, so let's try again that. Okay, so this is our answer. Sorry, there should be a space here. And then of course we don't want to actually want to see the progress of the points, so we just plot after the loop. Okay, let's make it a red, and let's say marker color is also red. Okay, let's run. Oh, sorry about that. So this should be color only. Okay, just remove this one. That's okay. Let's run, and that is our result. That's it. This is our results. This is our answer. The answer is for 142.7378 kilograms. In order for it to have a velocity of 36 meters after 4 seconds. Okay? Easy, right? So in your machine problems, you're going to answer 2 problems using 3 methods. First one is your analytical method. Second one is using the F0 function as discussed in your MATLAB modules. And lastly is what I want you to do is I want you to make a function that operates as a bisection. Given the function, anonymous function, the initial interval, as well as the stopping rate. Okay, and of course you have to show this some kind of a display at the end. Okay, which depends on whether that's a graph that's a display there on the command window, or both, depending on the problem that was assigned to you. Okay, so please check your blackboards. Okay, so that's all for now. Thank you for watching. I hope you learned something today, and I'll see you guys in the next video. Bye bye.